Hello everyone, welcome to the last session of this week. So in this session, we will focus on using nonlinear SVM to carry out a Raisin classification problem. So Turkey is one of the countries that ranks top to produce the grapes. So 37% are dried. So for these dried grapes, assessing the quality of the raisin is essential. There exists a traditional method that is by the human-made procedures, but this way is inconsistent and inefficient. So now we are thinking of some machine learning method to quickly and precisely evaluate the raisins, right? So there are two classes. So one is called the Bethany, and the other we call it the Casimir. So here we extract the features. The 7 features are here from area to parameter. So these are the classes. We have 2 classes, right? So the class 1 is a Casimir, class 2, class 0 is a Bethany. So we have 900 samples altogether. So now consider you are the information engineer. You want to train a nonlinear SVM to classify the raisins. So first, as we can see, we know the data. So this one we have covered in the last session, the banknote one. So I don't explain more. We read the CSV file and we make the matrix of features and labels. So we can see in this one, these columns are the features and these are the labels, right? And then we will train a nonlinear SVM. In implementation, this is very similar to the linear SVM, except the difference is we need to specify the kernel function. Okay, so first step, let's split the training data and test data. Right, so we can see using CV partition, we get the training set and the test set. Then we will use the training set to train the nonlinear SVM, and then we use a test set to test its performance. Right, so now we do the training. So we can see the function is here, similar as before, except here we use a Gaussian kernel as a kernel function, right? So the reason is that we don't know any information from this data set. So we first try the Gaussian one. But clearly you can try others, for example, the RDF, the polynomial, or linear. After the model, we call it SVM model, this one is trained, we can do the prediction. So we can see the prediction follow the same way as the previous session. We use this object, the test data, we can calculate the accuracy here. So after all these procedures, we found the accuracy is 86.2, right? So it looks like quite good. So all of the procedures you can see in the live script and try yourself. But now a question raised. So seeing 86.2 reasonably good, but can it be improved, right? So can we use other kernel functions? Will this lead to better result or not? Then an information engineer, he writes some code for the kernel selection. So let's see that. So after seeing this code, I have a few questions for you. First, we do the data as before. Then we select candidate kernels. So he wants to compare the polynomial, the RDF, and the Gaussian. Then he thinks that he wants to use cross-validation, right, to make a better estimation of each of the kernels, right? So he wants to do the run 20 times to see the cross-validation, how it goes. So his code is like this. For cross-validation, he repeats the following thing for 20 times and we get the average, right? So in this code, we can see we first split the data to training and test, and then we train the SVM model using the decided kernel, and then we predict using the test set. So we repeat this for 20 times and get the average. Okay, so this is and you can also try this program yourself. So then we will select a kernel based on the highest score of the accuracy. So after running this program, we get the result. The best kernel is RBF, and the average accuracy is 85.7. Right, so this is the result, and you can try it yourself. Now I have a few questions for you. The first question, what is the difference between this cross-validation and the standard k-fold cross-validation? And which one is better? Question 1. Question 2. We can see we tried the polynomial, the RDF, and the Gaussian kernel here, right? But we find the best one is RDF, and the accuracy is 85%. But the previous one using Gaussian is 86. So this means that using Gaussian kernel here, the accuracy is less than 85.2%, right, or 0.6%, right? Then, given this difference, which result do you believe more? Second question. Third question, so can we use the size of the box constraint, right? So this is a hyperparameter to trade off the margin and the misclassification, right? In nonlinear case, so this previously we talked about the soft margin classifier. That refers to the linear classifier, right? We allow some misclassifications, but now this becomes a nonlinear one. So can we still use a box constraint, the C value, right, to continuously improve the result? And why? Or how? How can this improve the result? Right. So these three questions are my questions for you to think of. So for the first two questions, I think you can answer them because using the knowledge that we provided in this week or previous weeks. And the third one, I didn't cover it yet. So now I can tell you the answer. So the answer is that yes, we can still use the box constraint to improve the result. So let's consider that when we use nonlinear classifier, we map from low dimension to high dimension, right? So, but maybe even in the higher dimension, we still can't use a strict hyperplane to divide the data. Maybe we can still allow some misclassifications in a higher dimension to make the result better. So the answer is yes, we can combine the soft margin with the nonlinear SVM, right? Okay, that's all for this week. Thank you very much. Bye-bye.